and we were talking about last time electron configuration. So remember that when we write electron configuration, there's really kind of two things that you need to know to be able to sort of correctly do it. Again, that s orbitals could hold a maximum of 2 electrons. The p subshell, which consists of 3 individual orbitals, could hold 6 electrons. The d subshell, which is basically 5 individual orbitals, could hold 10. And our F subshell, which is 7 individual orbitals, would hold a maximum of 14 if you fill that all together. You also want to do the correct order at which they do fill the atom, as we talked about. A reminder that you can sort of make that chart for yourself that tells you the order, again, by remembering that on the first energy level, all we have was S's. Not until we get to that second energy level that we have P's. Not until we get to that third energy level that we have D's, and our fourth energy level that we have F's. And really at that point, all you have to kind of do is just fill in the numbers with the letters underneath each of those. And again, remember, it goes to about 7, so you could just take them to 7 if you want. And 5F. And again, even if you again kind of took these guys further down the 7, it's okay because you won't get there anyways in most cases. So again, we do always start up on the top, and we then kind of zigzag back and follow the arrows. And again, that does give you the correct order, as you can see there, 3p to 4s, and then to our 3d, to our 5s, and then to our 4d, and so forth. So again, that's something you could create pretty quickly for yourself on the paper. And really all you have to remember is basically 1 through 4. And then again, just kind of fill in the numbers underneath and you'll have what you need. Now, when we write electron configuration, as we did, 1s2, 2s2, again, that is the way that we write it. We also talked about orbital diagrams. And orbital diagrams are either boxes or lines that represent each individual orbital. Remember that these first numbers here is the principal quantum number, that n, which is the energy level. The number on top is the number of electrons in that orbital or subshell. And obviously the letter is the subshell or orbital that the electrons are in. So if we were going to do the orbital diagram for this guy, we would have a box or a line for the 1s and a 2s. And as we talked about last time, typically speaking, if you're going to draw it correctly with energy, you would kind of stack them. But I'm just going to go side by side for space purposes here. Remember that when the first electron goes in, it does go in the upwards position, which represents that it has what is referred to as plus the 1/2 spin. And when we put the second electron in an orbital, it needs to go in the opposite direction there, and that would mean that it has minus 1/2 spin. That is what is referred to as having paired spin. Same thing for this guy. Now, if we did have like a 2p subshell, remember we would have 3 boxes or 3 lines, and whenever we have subshells that have obviously multiple orbitals that are the same, the way they fill is through what we talked about at the very end, I think last time, which was Hund's rule. And the idea there is we want to maximize parallel spin, which means that they do go in the same direction. So basically, when you got multiple orbitals in a subshell, we always fill them one at a time, and then we come back and pair them off. So always kind of go one at a time. That will maximize that parallel spin, and then you come back through and kind of pair them off as you need. Any questions on that there? All right, so I think we got through carbon, so might as well finish the first 10 there. So let's take a look at nitrogen, which is atomic number 7. Again, that means that a neutral atom, the atomic number, which is the number of protons, will also tell you the number of electrons. So it should have 7 electrons. Once again, we're going to, as we've been doing, starting up here. So that's going to give us 2. We then need to zigzag back. That'll give us another 2. That is 4. And here we will be able to kind of get into our 2p subshell by going through there. So This will give us, in terms of electron configuration, 1s2, 2s2, 2p3. Once again, at this point, we have 5 electrons in the second energy level, and we have the maximum of 2 electrons on the first energy level in this particular case. In terms of our orbital diagram, again, I'm just going to draw it straight across instead of upwards. We would have a 1s, we would have a 2s, and once again, we would have 3 lines to represent each of the p orbitals, like the px, the py, and the pz orbital. And in this case, we would go up, down, and once again here, we're going to follow Hund's rule and maximize the parallel spin, and that's going to go 1 into each of those. Any questions on that one there? Obviously, from the picture there, we can see that we are pretty much halfway filled with our 2p subshell. We could put another 3 electrons in there if necessary. So let's continue on and finish the rest of it, which is oxygen next, I think. So oxygen has 8 electrons. Once again, we're going to be good by coming here. That way we could use 2, zigzag backing. 2 more is 4. And again, we have the availability of 6 that we could put in there. And that again should get us to where we need to be. So continuing on, we would end up with 1s2, 2s2, 2p4. Once again, at this point, we now have 6 electrons on the second energy level, 2 in the s orbital and 4 in the p orbital, and still are 2 on the first, which is, again, the maximum you can put in there. Here we would go with our oxygen, 1s, 2s, and our 2p subshell. We're going to go up, down, up, down, up, up, up. At this point, we have no choice, but we do come back to the left, and they do always sort of feel left to right there when you're kind of drawing those pictures for the orbital diagrams. Any questions on that one there? All right, so next one is fluorine, which is number 9. And once again, we would end up here at 1s2, 2s2, 2p5. We're now up to 7 electrons in the second energy level and 2 in the first. And at this point, we would have, for our orbital diagram, up, down, again, up first all the way across, then down, and then down. At this point, you could also see we are down pretty much to one more spot there that we could put an electron in that p subshell before it's full. And that does happen at neon, so might as well just finish out the first 10 here, which is neon. Let's take a look at that one. So neon would get us filled, so 1s2, 2s2, 2p6. Once again, you can count the top numbers to know how many electrons should you have filled. So 2 and 2 is 4 and 6 is 10 total that we put in there. At this point, we now have 8 electrons in the second energy level, and we have 2 electrons in the first energy level. And in terms of our orbital diagram here, we'll go up, down, up, down. Once again, up first, and then come back and pair it off. At this point, we obviously cannot put any more electrons into our 2p subshell as it's full. The next place we would need to go is the 3s orbital next after that. Yeah. Question on electron configuration, orbital diagram. Questions? Yeah. All right, so let's take a look at, why don't you do, okay, so let's take a look. So we're at 18 in this case. So always, like we've been talking about, we're going to start up here. We're going to go this way. That's 2 that we could use. That's 4 with 2 more. That's another 6, which gets us to 10. We then would have to come here to 3s, which would give us 12. And we then could go through here to our 3p, which will get us to our 18, in this case, using it all. So we should have 1s2, 2s2, 2p6, 3s2, and 3p6. In this case, we have 8 electrons on the third energy level, 8 on the second, which is actually the maximum for the second, and 2, which is the maximum there for the second energy, or first energy level in this particular case. Question on the configuration there. Once again, our orbital diagram, if we don't draw it upwards for energy's sake, just to kind of save some room here, we'll need 3 there. We'll need that, and we'll need, not that, just 3p there. So we'll go 1, 2, up, down. Once again, this is going to fill one at a time, and then come back, up, down. This guy will also fill one at a time, and then come back through again, just a scratch out there. Any questions on that one there? So if we look at, for example, potassium, which is next there on the periodic table. We'll come back to that. There you go. So if we look at potassium, which is number 19 on the periodic table, and we do its electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 in this case. Again, at this point, remember a couple of things. The 4s does come before the 3d as it's lower in energy, so it will get those electrons first before we go into the 3d because of it being lower in energy. Now, when we look at this configuration up until this point here, that is the one we just did a second ago, which is 18 electrons. If you count up all the top numbers there, you get 18. And we know that that is argon's configuration. So we could do a shorthand where we put basically argon in brackets to indicate the electron configuration for argon. And then we would just kind of continue on with the electron configuration here. And that would be sort of a shorthand for electron configuration for something like potassium. Argon is a group 8 element, which means it's a noble gas. And that is what needs to go in the bracket. So sometimes people refer to this as the noble gas configuration when you're kind of doing it. It does need to be a noble gas that goes into the brackets. And it's the noble gas that comes right before the element you were going to write the electron configuration for. So for example, if we were going to do, say, sulfur, and sulfur over there is 16. And if we look at the periodic table and kind of go backwards, we end up back at neon before sulfur. And in this case, we would actually, we wrote out its electron configuration, 1s2, 2s2, 2p6, 3s2, 3p4. We would take this part of it here, which would be neon, and then 3s2, 3p4. So again, it's got to be that noble gas that comes right before it. If we did something like sodium, which is 11, 1s2, 2s2, 2p6, 3s1. Again, neon comes right before it. 3s1 is our sort of shorthand here. So it's always got to be the noble gas that goes in those brackets for just kind of the shorthand. And it's got to be, again, the one that comes before it on the periodic table, not after it, obviously. Any questions on the shorthand there? Yeah. Okay. Yeah. Yeah. Either or is perfectly fine as long as the question just simply says give the electron configuration. If it says give the electron configuration, but like don't use noble gas configuration, then you should do the 1s2, 2s2. But if it's just like a plain straight up give the electron configuration, either one is acceptable. Yeah. Other questions? Okay. All right, let's talk a little bit about transition metals. Transition metals are basically where we get into our d orbitals, and transition metals again are those guys between group 2 and group 3 on the periodic table. and they have filled or incompletely filled d subshells. Now, there are some exceptions that you come across in the transition metal region. If you were to just kind of follow our little chart there, going zigzagging back and forth, there's actually some exceptions to the electron configuration rules based on sort of experimental observations where they have found, for example, these two that you'll be responsible for, which is chromium number 24 and copper number 29, that they're actually a little bit more stable in a different configuration than you would get if you just strictly followed the chart. Now, it happens here around that 4s and 3d orbitals. And remember, in terms of energy, when the electrons are being filled, the 4s is actually lower in energy than 3d, but they're actually very close in energy. They're not too far away from each other in terms of energy difference between the s orbitals and the d orbitals. So what happens is if you took something like chromium there at 24 and you followed our chart, you would end up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4 in this case. Now, basically, that means you would end up with something like this. And what they've found experimentally is actually chromium is a little bit more stable with an extra electron sort of promoted up to the d orbital. And it's able to do that relatively easy because, again, they're very close in energy anyways, those orbitals. And as we'll talk about here in a second, what actually happens when you actually start putting electrons into the d orbital, they actually switch in energy. So they actually do a little switch those orbitals. And what ends up happening is the 4s, once you start filling the d's, actually ends up being a little higher in energy than the 3ds. But when you do fill the atom, the 4s is lower in energy, so they do get the electrons first. And that's why when we write electron configuration, we write it like we've been doing, and you should do for this class and all chemistry classes you pretty much take. You write it based on filling order, which is 3s2, 3p6, 4s2, or whatever it may be, and then the 3ds. You will, though, if you look around, sometimes see people write electron configuration like all in order, it looks like all the 1, 2, and they'll go like 3s2, 3p6, 3d4, 4s2, and they'll put them all kind of in order. And that's technically not wrong because it is based on energy rather than filling order after the electrons are in there. But it's wrong for this class and probably every chemistry class you take because we write it based on filling order. So it's technically not wrong, but it is actually wrong in terms of all the chemistry classes you ever take. I think I've only taken one chemistry class ever where they made us write it that way based on energy rather than filling. So all chemistry classes do it the way we're learning here. S's first, then D's. But what the exception is actually right here. So as you can see on the bottom, this is argon's configuration. So chromium is actually argon 4s1, 3d5. So what that essentially does is it maximizes, if you think about it, all those parallel spins, right? It puts basically one electron in each of them. They're all heading in the same direction. So kind of follows that Hund's rule and maximizes it. Copper is pretty much the identical exception. So copper, if you were to follow our normal sort of chart, you would end up with argon 4s2, 3d9. And again, we're going to have for copper one electron kind of going upwards there, and that will give us our argon 4s1, 3d10. It sort of fills in the d orbitals and actually gives the s orbital at that point an unpaired electron, which ends up being actually higher in energy. And again, that makes it a little bit more stable in that sort of case. So these are two exceptions that you need to be aware of. You need to be able to write their electron configuration correctly, chromium and copper. Truth be told, if you look at the periodic table and you look where chromium is and copper is, and if you go down and in between those two, it is littered with a bunch of exceptions in that area. Something like silver is an exception. It has a very similar exception. It has one extra electron up in D. PD actually has no electrons in their S's. They've all went up to the D's and so forth. So if you kind of go below chromium and copper on the periodic table, in reality, there is a lot of exceptions that occur in that area. But for our class, you'll just be responsible to know chromium and copper. For everything else, you could just write it based on our little chart there, even though in reality it might not be correct because there is those exceptions. I think maybe it might be on here. You can see them here, maybe. Where did I pass that slide there? No, that was not the right one. All right. Here you go. So here again, you can see the exceptions. And again, if you go below them, there's many more that have it. But for us, just those two in blue and the ones we just talked about, which is chromium and copper, you do need to be aware of. Here's actually a chart of a few more, not all of them, but here's a few more that's been found experimentally to be different. Like I said before, you can see PD will have actually no electrons left in the S. They'll all be promoted. Here again, we got some extra electrons heading over to our Ds. So for us, chromium and copper, but as you can see there, there's a bunch of them underneath them on the periodic table that actually are exceptions in real life. The lanthanide series and actinide series, those guys on the bottom is where we get into our F electrons or our F orbitals, and they have incompletely filled F orbitals. And again, if you follow your zigzag thing, you should be in good shape. Actually, on this one, you can kind of see some of those exceptions we were talking about. Again, you can see silver is an exception, or PD. And again, there's some other ones underneath chromium as well. So there's a bunch of sort of exceptions that do occur. Now, if you want to, you can use the periodic table, for example, to count off electron configuration if you kind of know what you're doing. I don't know if I would recommend it in all places or all electron configuration, especially if you're not 100% sure what you're doing. But you could use it to check a lot of things and hopefully make sure that you're doing it right. So the period numbers that we see on the periodic table, those represent the N numbers, the energy levels basically, right? So 1 is our first energy level, 2 is our second, and so forth. So there's 7 of them. Now groups 1 and 2 are our S blocks, and S could hold 2 electrons, so that is 1 and 2 electrons essentially. Groups 3 through 8, that is our P block on the periodic table. P subshell could hold 6, so 1, 2, 3, 4, 5, and 6 boxes. Our transition metal that we just talked about could hold 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And these are our F block down here. And you could count it, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 electrons. So for example, if we looked at sodium, which is right about here, what we would do is we would start up on top here. That is 1s2 to helium. That is now 2s2 to there. That is now 2p6 to the end. And now this is now 3s, just one box in. Good thing, because I was running out of room. 3s1 there at the end. Now, if we went to, say, something like chlorine, which is right about there, we once again would start at the top left there. And we would go 1s2 to there, 2s2 to there, 2p6 to there, 3s2 to there, 3p1, 2, 3, 4, and 5. Yeah. And you again could literally just kind of count off the electron configuration from the periodic table. The reason I do say that you might not want to use it for all of it, or you need to be really careful. Let me just kind of clear all my scribble out. Let's just say we wanted to do somebody like iron, which would be right about there. Yeah. So once again, this is 1s2. This is 2s2 to there. coming across here, that's going to give us 2p6. That is 3s2. That is 3p6 to there. That is 4s2. And this is D, and as it says there, that D is not 4, but it is 3D, because that is where the D orbitals begin. They are actually one behind the period number. That's 3D, this would be 4D, and so forth coming down, which is why when we did our chart, 3D, 4D, 5D, and we stopped at 6D, yeah. By the way, this down here is our Fs. F start at 4, yeah, that's 4F and 5F. Also why our chart stops at 5, by the way, because we're out of elements, as you can see there. Those technically, though, go over here, which is period 6 and 7. They're actually 2 behind the period number back there. So it does get a little crazy in that kind of middle region if you're trying to count off the periodic table and do electron configuration. You got to really watch out what you're doing. Stuff on the outside, you could probably be pretty safely and get the right sort of electron configuration if you wanted to count it. So that would be obviously 3D 1, 2, 3, 4, 5, and 6. And then we would have our electron configuration. Any questions on that there? So again, you can use the periodic table to do your electron configuration if you like. Any questions on electron configuration, orbital diagram? Obviously, you need to be able to do that. Let's talk a little bit, though, before we continue on, about what happens when we do get things that have charges. So if we do have things that have charges, which are obviously ions, we do have to adjust the electron configuration. So for example, if we had sodium, which is 11 with no charge, 1s2, 2s2, 2p6, 3s1. Sodium, which is group 1, would normally form a +1 charge. And +1 charge or plus charge means it has lost electrons. And a +1 charge means it has lost 1 electron, which means it will actually only have 10 electrons at this point. And we would have to adjust electron configuration, 1s2, 2s2, 2p6 in this case. That is 10 electrons. That is also the same as neon, right? That's the same electron configuration as neon in this particular case. If we look at nitrogen with no charge, which is 7 electrons, 1s2, 2s2, 2p3. Nitrogen will make nitride, which has a -3 charge. That is negative, which means it has gained electrons. It's gained 3 electrons. It also has 10, which means its electron configuration 1s2, 2s2, 2p6 in this case. That is also 10, which means it has the same electron configuration as neon. All 3 of those things, neon, sodium with a +1 charge, nitride or nitrogen with a -3 charge, they all have the same electron configuration. That is what is known as being isoelectronic with each other. Isoelectronic means that we have things with the same electron configuration. It is also the whole purpose of bonding. It's the whole purpose of ionic bonding. It's the whole purpose of covalent bonding. Everybody wants to achieve noble gas configuration because the noble gases are chemically inert. They are super stable. So the whole purpose of all bonding is for everybody to end up with the same electron configuration as those noble gases. The way that metals do it in an ionic bond, for example, is they lose electrons and they back up on the periodic table to the noble gas that comes right before it. So if you look behind sodium, the noble gas is neon that comes right before it. The way nonmetals do it in an ionic compound is they actually gain electrons, and that moves them forward on the periodic table to the noble gas that comes after them. So if you look at nitrogen, neon comes after it. So by gaining those 3 electrons, it becomes the same electron configuration as neon in this particular case. In covalent bonding, which we'll also talk about, they do that by sharing electrons, not actually transferring electrons like we have in ionic compounds, but they achieve the same thing. They achieve basically noble gas configuration by sharing electrons. questions on that there? Now, when we have something that does have a charge like that, we do have to take into account it. Transition metals, though, are a little different in terms of what happens when they do get a charge. And before we go on with that, what I was going to ask, that I could have remembered, now I remembered, is all three of those things, right? The sodium and the nitrogen, just to remind you, they do not become those elements, right? And they only become the same electron configuration. Why do they not become those elements? Why are they still sodium and nitrogen, even though they have the same electron configuration as neon? That's exactly right, right? So what we talked about was it is the protons that determine what element you're talking about, and every element has different numbers of protons. So we're not changing any of the protons, so there's still sodium and nitrogen. They just now have the same electron sort of configuration as those noble gases. Now, as I mentioned before, transition metals are a little bit different in terms of what happens when they sort of gain electrons, or sorry, not gain electrons, lose electrons. And it has to do with our 4s. We can look at this part of it and 3D example. So as I mentioned before, in terms of energy and electrons going in, they will go into that 4s first and then start filling your 3D. When we do start filling the 3D, as I mentioned earlier, these guys will actually switch places in terms of energy, and our 4s electrons actually become higher in energy. And that's really important for example, when things lose electrons, things typically lose electrons, the highest energy electrons are lost first because they're not held as tightly, so they're able to be popped off pretty easily and lost a lot easier. So that means when we get to a transition metal, let's just take iron, for example, which is 26. We did the electron configuration for iron. I'll do just shorthand so I won't write it all out. We have argon, 4s2, the one we just did there, 3d6. So what happens is when iron becomes, say, a +2 charge in this case, and let me actually just fill this in with all of its electrons. So when iron becomes a +2 charge, it has lost 2 electrons and now actually has 24 electrons. When we go to write the electron configuration for this transition metal, because that switch in energy occurred, it's actually going to take out those higher energy 4s electrons first, and we will end up with a configuration of argon 3d6. So transition metals will always lose their s electrons first. And kind of an interesting thing about transition metals is they also have those d electrons that they can lose as well. So for example, iron's a good one. If we want to go to iron with a +3 charge, it's now 23 electrons. We again would take out the 4s2, but now we need to lose one more electron, and that's going to come right here. We're going to take out that electron from that spot, and now we will end up with argon 3d5. That is also why, by the way, that transition metals typically have the ability to make a variable type of charge because they got some of those extra d electrons that they could use to kind of lose, and they're able to make the kind of variable charge. So all d, our transition metals, will follow that pattern. They can essentially all transition metals will essentially lose their s electrons first, and then when they go, they will then jump in if need be and take out some d electrons at that point. Any questions on that there? Yeah. Yeah. This one? Yeah. Now, for example, why don't you try nickel with a +4 charge. Nickel is on the periodic table 28. So write the correct electron configuration for nickel. And while you're at it, why don't you also do it for calcium with a +2 charge. And we'll do Eh, we will do F minus. Calcium is 20 and F is 9. Okay, so let's take a look. We'll start with nickel. And why don't we just start with nickel with no charge? So nickel with no charge is, what we got there? 28, I think, yeah. So that's going to be argon. If I kind of did the shorthand there, so I don't have to write it all out there, 4s2, 8, 3d8. Obviously here, nickel with a +4 charge would have 24 electrons, as is lost 3 electrons. And if we just kind of sketch out our orbitals at this point, once the Ds have those electrons, we will have something that looks like this. 5, 6, 7, and 8. And again, this is after it's been filled, so we have that switch in those energy levels of the orbitals. It will then lose, obviously, here are 2 out of our S, but we still need to lose 2 more, so it's going to take out that one and that one, so we will lose 2 out of that one, and we will end up with argon 3d6 in this case. Any questions on that there? All right, going to calcium. Calcium with a +2 charge. Calcium with no charge is 20, and that means it should have 18 electrons, right? And again, with no charge, it is 20, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Here at 18, it is going to take out the last ones there, which is the highest energy level. That's going to leave us basically that, 1s2, 2s2, 2p6, 3s2, 3p6, which is 18, which is again the same electron configuration as argon in that case. Any questions on that one there? And lastly here, we got our fluorine, which is 9, 1s2, 2s2, 2p5. Fluorine with a -1 charge means it has gained 1 electron. That's going to take us to our lucky number 10 there. 1s2, 2s2, 2p6, or that is neon's configuration. Noble gas configuration, gets to noble gas configuration. How about my transition metals? Do they get to noble gases? They actually don't, right? They would have to lose, for example, they would have to lose, say, something like zinc, but it has to knock off about 12 electrons and have a +12 charge, which probably is not going to happen. So typically speaking, transition metals don't end up back to noble gas configuration because they have a lot more valence electrons available to them, like the S's and the D's. Your representative metals like calcium, potassium, group 1, group 2, group 3, they do usually end up back there at a noble gas because it is going to allow them to do so. That also means that when we take out these electrons for transition metals, not always the last ones that are representative elements. They will probably be the last ones written in the configuration. Question on things with charges in electron configuration. Yeah. All right, I'm pretty sure I read all over this, and maybe I didn't. Hey, wait, no. All right, we're now going to talk about some periodic trends and some other parts here of the periodic table that will help us understand, again, what's going on really with bonding. First off, our valence electrons. Our valence electrons are our highest energy electrons. So when we look at something like what we have there, which is our nitrogen 1s2, 2s2, 2p3, remember that these numbers in front are the energy levels, and these guys here are the highest energy levels in the case of nitrogen, which is 2. And at each of those there, we have 2 in the S and 3 in the P. That is 5 valence electrons that nitrogen would have. In this case, these lower energy electrons, which are closer to the nucleus, are what are referred to as core electrons. Those are the ones that are not involved in bonding because, frankly, they're just right smack there next to the nucleus, and they're held super tightly. and good luck trying to get rid of those. There's not going to happen. So when we talk about bonding and stuff like that, it is just those outermost valence electrons involved. And you could get it from the electron configuration. If you look at sodium that we just did, 1s2, 2s2, 2p6, 3s1, that is the third energy level now, and we only have one electron. So that would be one valence electron. Again, our core electron is a little bit lower in energy. Who wants to write the electron configuration for all this stuff to figure out how many valence electrons? Nobody wants to do that, including yourself. So clearly we could do it much easier, and we could do it by looking at the periodic table. And the periodic table will tell you how many valence electrons each element has. It is equal to the group number. So 1, 2, 3, 4, 5, 6, 7, 8. So when we talk about our representative elements, everybody obviously in group 1 has 1, 2, 3, 4, 5, 6, 7, and 8 valence electrons. So if you look at fluorine, that is group number 7, so it has 7 valence electrons. If you look at chlorine, also group 7 has 7. Carbon, which is group 4, has 4 valence electrons. Again, for carbon, 1s2, 2s2, 2p2. These are the 4 valence electrons there in carbon in this particular case. Now you might be asking what is the deal with the transition metal region. Who knows? No, I'm just kidding. So the transition metal region is basically what we were just talking about when we did our charges, right, for our transition metals. So they typically will lose the s electrons, right? And they also have the ability to lose the d electrons as well. So if you want to know for your transition metals, you should actually just revert back to just a regular old 1 through 18 numbering, and that will get you what you need. And what I mean by that 1, 2, and then go. And again, this is just for transition metals. So really, you know, this would be 3, 4, 5, 6, 7, and so forth. Really, it's kind of 3 through 12 there. You know, you could revert back to that. So if you look at iron like we've been looking at, and if you count the spots there for iron, that is 3, 4, 5, 6, 7, and 8. Basically, if you just went 1 through 8. And if we look at iron, what we just wrote as configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6 there. Right here is irons, basically valence electrons. The S's that are going to be lost first, followed by obviously the D's if necessary. So transition metals, if you want to go off the periodic table, you should just go left to right and really just number it all the way through. Just don't skip any column, and that will get you the right ones. Obviously, when you jump back to here, where boron is, you need to go back to the A numbering of 3, 4, 5, 6, and 7, and 8, and stuff like that. But so basically for transition metals, kind of like 3 through 12 will work in most cases. Any questions on that there? All right, so let's talk a little bit about metals and nonmetals. As you saw in one of those experiments, maybe you did last week, when we go down a group, metals typically will give away their electrons a lot easier. And maybe you saw the difference, you know, forget where you looked at in that experiment, but whatever. But maybe sodium, potassium, and reactivity of those guys. But in group 1 there, we see cesium will give away their electrons a lot easier than lithium. And what we find is in terms of nonmetals, our most reactive nonmetal is actually upper right of the periodic table where fluorine is. And we stop at fluorine because to the right of fluorine is the noble gases, which are chemically inert, so they're not very reactive at all, so they're just hanging out. So fluorine's our most. That you maybe saw when you did the halogen one, right? In that experiment, we had the different layers. You should have saw reactivity. Bromine was less reactive than chlorine, and iodine was less reactive than bromine. And so reactivity increased as you went up that group in group 7. Now, there's several reasons why that occurs. So let's talk about some of these periodic trends and the reasons why it occurs. So the first thing we're going to talk about is what's known as Z effective, and that is what is sometimes referred to as effective nuclear charge. And to sort of demonstrate what effective nuclear charge is, Let's just take a pretty simple example of lithium. Lithium has 3 electrons, and if we write the electron configuration, 1s2, 2s1. Lithium, which is group 1, has 1 valence electron, which is that guy right there, and it also has 2 core electrons. Right. Now, if we were to draw sort of a picture of lithium, its nucleus would have a positive 3 charge because of its 3 protons that are hanging out there. And I'll just sketch it like this for the purposes of this demonstration here. On the first energy level, we got a couple electrons in that area. Not really sure where they're at, but they're somewhere in that area there, near the nucleus. On the second energy level, which is a little further away from the nucleus, we have our valence electron kind of hanging out over there. So remember that when we talk about electrostatic attraction, which is a fancy way of saying positive, negative attraction, right? Opposites attract. The strength of that attraction increases with the charge. So something that's +3 and -3 will be held together a lot tighter than something that is like -1 and +1. So those kind of core electrons, which are here, they are pretty much filling the full brunt of that +3 charge. So they're going to be held really, really tightly because they're pretty much front row center to kind of like the nucleus. They're pretty close to it. They're going to get that full brunt of that +3 charge. Now, when we talk about our lonely little valence electron out here, he is not going to actually feel the full brunt of that +3 charge. He's going to experience what is known as shielding. And this valence electron is actually shielded from the full brunt of the +3 charge in the nucleus. It's like if you went to the movie theaters and you could still pick your own seats. They don't let you do that anymore here. So you get there early and you get the seat right in the middle, right? Perfect view of the screen, nobody in front of you. And right before the movie starts, somebody comes and sits in front of you with a giant hat. And they just shielded half of the screen, right? You can't see anything. And that's sort of the idea here. Because we have these lower energy electrons, they're actually just kind of blocking that +3 charge, the full strength of the +3 charge. They're kind of absorbing a lot of it. And by the time what gets through them is now something that's a lot less positive. And because of that, it's actually not going to hold that electron as tightly. You could actually calculate what it's filling by doing the calculation. So for example, if you wanted to calculate the Z effective, it is the number of protons or positive charge, like would be +3 in lithium, minus the number of electrons, or added the number of electrons that we have, which is -2 charge. So that outer electron is actually only feeling a +1 attraction to the nucleus versus a +3 attraction. And because of that, it's not going to be held as tightly, and that is why that valence electron is involved in bonding. And that's why the core electrons are not involved in bonding, because they're just like stuck kind of to the nucleus in a sense from that positive charge and attraction. Any questions on that there? What happens is, when you look at the periodic table, Z effective actually increases as you go up and to the right and decreases as you go down. And what that means is if you look at the atomic number as you go to the right on the periodic table, it actually increases, right? So the number of protons increase as you go to the right on the periodic table. That means that those guys on the right-hand side on the periodic table actually has a greater positive charge in the nucleus. And even those outer electrons now will still feel a much stronger positive attraction than they will if they're on the left side of the periodic table when they have a smaller positive charge in there. So that affects things like we will see, like size, for example, right? Those guys on the right with a bigger positive charge is going to bring even the outermost electrons closer in, because there's going to be some attraction more than what you see on the left-hand side of the periodic table, where it still has a positive charge, but it's not as big as what you see on the right-hand side. So those outer electrons don't get pulled in as much. Question on that there. Now, another important trend is what is known as ionization energy. Ionization energy is the energy required to remove an electron from the gas phase of an atom. When we talk about ionization energy, we think about cation formation. Those are positively charged guys. That's what happens. So this is the energy required to remove an electron. If you have a high ionization energy, that means it's going to be super hard to lose an electron. If you have a really low ionization energy, it means you could just look at it wrong and the electron will just pop off. It's not a big effort to remove an electron if you have a low ionization energy. By the way, just so you know, electrons do come off one at a time. They don't just all pop off. So for example, if you looked at something like magnesium, the first thing that would happen is magnesium would actually just lose one electron. And then this guy would require a certain amount of energy, which is known as the first ionization energy. So the first ionization energy for any element is the energy required to remove the first electron. Then what will happen is this magnesium with a +1 charge will pop off another electron. And that is what is needed to do that is the second ionization energy. And then maybe this guy, I'll just go down here, that has 2 electrons lost, will lose another electron. And that is what is known as the third ionization energy. If you had to take a guess, which one is easier to do? Is it easier to remove the first electron or the second? It is easier to remove. I think I saw a finger of 1. So it is easier to remove the first electron than the second. First electron is neutral. When it loses an electron, what happens to the size of a cation? Does it get larger or smaller? Yeah, it shrinks, right? The electrons get closer. Now those outer electrons now just move closer to the nucleus, which means harder to remove the second one. Lose the second one, everybody shrinks in again. Harder to remove, right? They're closer to that positive charge. So it gets harder and harder every time you rip off an electron. And comparison of the first ionization energy to the second to the third would be a lot more energy needed than the first ionization energy to try to rip off that third electron. In some cases, it really doesn't happen. And this is a case that you would not go to the third one because if we look at the electron configuration for magnesium, 1s2, 2s2, 2p6, 3s2, magnesium has how many valence electrons? Magnesium is group number 2, so it does have 2 valence electrons, right? And that is these right here. That, by the way, takes us to here. When I get to that third electron, I am now into the core electrons. The energy jump is enormous between like the second and the third. So for example, I don't know the numbers off the top of my head, but maybe it goes from, for example, 500 joules of energy for the first electron to maybe like 1,000 joules, and then it goes from like 1,000 to like 11,000 joules. So it's a really big jump to try to take off the third electron. So typically what happens is as you get into those core electrons, the energy demand to try to remove that electron gets so high that it doesn't happen under normal conditions. This is also why certain elements will make fixed positive charges, like magnesium will only make a +2 charge for that reason, or one of those reasons, because it will not go any further. It's just not energy efficient to try to remove those. We stop, say, with a +2 charge for something like magnesium. Question on that there. The general trend for ionization energy is as you go to the right, it increases on the periodic table, and as you go left and down, it decreases. So metals typically will be on the left there. They typically will lose electrons because it's not too hard. Non-metals upper right of the periodic table, typically super hard to try to remove electron. It usually doesn't happen because of the really high ionization energy that they have. Question on that. And here's the chart. Actually, here's the numbers. Let's see how off I was. That was not too, well, kind of close. So 735 for that first electron in magnesium, 1445 there for the second. And you can see it jumps about 7-fold there to about 7,700. You can see aluminum, which is why it forms a +3 charge, First electron, not too bad. Second, a little bit worse. Third, worse. But then it goes from like 2,700 to 11,000. So it's a tremendous jump. And that's the fourth electron in aluminum, which is a core electron. And that's why it's not going to happen. And that's why aluminum also sort of taps out there at +3 when it loses those electrons as well, because it's not going to be able to lose that core electron. Another important trend is electron affinity. And electron affinity is actually the energy change that occurs when somebody gains an electron. So we think about anions when we talk about electron affinity, because those are things that gain electrons and become negatively charged. It's really not a perfect trend, but the overall trend of electron affinity is it increases as you go up and to the right, decreases as you go down and to the left. It's not perfect. So for example, if you looked at group 7s, each electrons, it kind of from the bottom up goes up, then it kind of drops back down, then goes back up in terms of the change. So it's not like a perfect sort of thing, but that's the general trend. Affinity in general means that you like something, right? So those with high electron affinity like to gain electrons. They're pretty successful at doing so. And something with a high electron affinity would be something that would want to gain electrons pretty easily. Another really important trend, which I'll write here, why not, is electronegativity. And electronegativity is the different than electron affinity. So electron affinity you could kind of think of as it's already done, it's already gained electron, and the changes occurred in terms of energy. Electronegativity is a lot what we see with bonding, which is the ability to bring an electron towards itself. So electronegativity is the ability of an atom basically to bring electrons towards itself. When you look on the periodic table, it increases as you go up and to the right and decreases as you go down and to the left. Fluorine is the most electronegative element that you could have. And again, that's pretty much as far upper right as you could go on the periodic table. That's not a noble gas. And it is the one that's the most electronegative. Now, all of these periodic trends that we've been talking about basically affect also the size. And by the way, when somebody gains an electron and becomes an anion, does the anion become smaller or larger than the neutral atom? It does become larger again because it's the opposite of the cation. It's gaining electrons, so as the electron cloud starts to grow, so the overall size of the negative ion is larger than the neutral ion. So these guys have also affect atomic radius, which clearly I wrote on this page, so we get rid of that. And the atomic radius actually is the one that decreases as you go up and to the right on the periodic table. So things get smaller as you go up and to the right on the periodic table. One of the big reasons for that is what we talked about at the beginning, which is the effective nuclear charge. So as you go up and to the right, again, we're getting more positive charge, less overall electrons, going to be able to bring those guys in a lot closer to each other, and it's not going to be as large. And that's what we see here up and to the right. Size gets smaller, and down and to the left, it gets larger. And again, that effective nuclear charge increases as you go to the right. And again, that's going to pull out those outer electrons much closer to the nucleus, even if they're far away. And that's going to result in a smaller size. When we take all of these sort of trends together, it does make sense in terms of what we know happens for metals and nonmetals. So let's just draw a generic here. Yeah. Let's just draw a generic periodic table, right? Also known as just a big box on the screen there. And we put in all of our trends that we just talked about, which is Z effective, increasing as we go this way, decreasing as we go this way. We did ionization energy, increasing as we go this way, decreasing as we go this way. We did electron affinity, increasing as you go this way, decreasing as you go this way. We did electronegativity, increasing as you go this way, up and to the right, decreasing as you go down. And lastly, our size, our radius, actually decreasing as you go this way. So when we look at all these sort of periodic trends together, it does make sense when we look at somebody that is in the upper periodic table. That is where we find our nonmetals. Our nonmetals have a higher effective nuclear charge, which is going to bring everybody closer to the nucleus, going to result in a smaller size for the atom. They have the properties of high ionization energy, which means good luck trying to remove an electron. They have high electron affinity, which means they want to gain electrons and they're pretty good at gaining electrons. And they have high electronegativity, which means they want to keep their electrons and they also want your electrons. That's basically all the properties that nonmetals have. And that's why what we see with nonmetals is they want to keep their electrons, they want to take other people's electrons. That's why nonmetals typically become anions and have negative charges because they're not going to give away their electrons. They're more apt to gain electrons. As we go to the left on the periodic table where we have metals, we have things that have a low effective nuclear charge, which means the outer electrons are not going to be that close to the nucleus. They have larger size, which means, again, those outer electrons are further away from the nucleus. They have low ionization energy, which means you don't have to convince them really hard to lose their electrons. It doesn't take a lot of energy to do so. They have low electron affinity, which means they are not looking to gain electrons. And they have low electronegativity, which means they're not looking to take anybody's electrons either. And all of those things is what we see with metals, which is they tend to just give away their electrons. So these are the reasons why metals will give away their electrons, and they typically become cations. That is also why you get an ionic compound when you mix together a metal and a nonmetal, because that is like the perfect storm of you have the metal willing to give away its electrons, and you have the nonmetal saying, thank you very much, I'll take those, no problem. And you get that complete transfer of electrons. And that is the basis of ionic bonding, where those two guys get together. That's really what facilitates the electrons moving from one to the next, is those periodic properties, electrons jumping from the metal to the nonmetal. That's also why when we talk about covalent bonding, which is between two nonmetals, they're basically in the same spot on the periodic table, which means when two nonmetals get together, neither one of them is going to lay up their electrons to either, right? They're like, no, thank you. I want mine. You keep yours, but I want to also take yours as well. So what happens with that conversation, which is the actual conversation they have, and they go, all right, we'll just share. Yeah, why don't we just share? So they will not transfer, but they can kind of compromise and go, neither one's going to give it up. They're going to actually share the electrons in that case. And that's why we get sharing of electrons and covalent bonding between two nonmetals because of the periodic trends. But we get an ionic bond and transfer of electrons when a metal and a nonmetal basically come together. Any questions on any of that there? All right, so a couple of concept checks here. Which should be the larger atoms, sodium or chlorine? Again, if we look at the periodic table, sodium and chlorine are in the same group. I'm sorry, they're the same period. And that group going up and down, they're in the same period. And obviously chlorine is further to the right, which means it should be the smaller atom, and sodium should be the larger atom in that case. Which one is the larger atom between lithium and cesium? Those guys are in the same group. Group 1 there. Lithium's on top, cesium's on the bottom, and cesium should be larger as it goes down. That's also why those periodic trends that we just talked about, we talked about the metal's most reactive spot for a metal, lower left of the periodic table, because that's where all those periodic trends come together. That guy's like, just take the electrons, I'm good. And most reactive non-metal, top right of the periodic table, again, because it has all those trends of I'm just going to grab any electron I get near me, right? And that's going to make it really reactive. And that's what you saw in that experiment in group 7. As you went up, the chlorine more reactive because of those properties. Which one is larger? 1s orbital in hydrogen, or the lithium 1s orbital? Now, when we talk about that, they're both a 1s orbital. The difference, though, right, between hydrogen and lithium is actually the positive charge of the nucleus. Lithium has that +3 charge. So hydrogen has the +1 charge. So that 1s orbital in lithium is actually going to be pulled closer to the nucleus than the attraction there. In hydrogen, that's going to give it, not drawn to scale, obviously, a much larger 1s orbital there than we see in lithium. Which one will be lower in energy? It's actually going to be the lithium for this same explanation, because the lithium 1s orbital is going to be pulled stronger by the +3 charge. It will actually end up being lower in energy than the 1s of the hydrogen. That's not going to be pulled down or closer than the +3 charge there. Any questions on that there? Now, in terms of ionization energy, oxygen, fluorine, and sulfur, if we look on the periodic table, this is their location. And in terms of ionization energy, it increases as you go up and to the right. So sulfur, oxygen, and fluorine should be the correct order, fluorine being the most in terms of ionization energy. Now, in terms of size, it actually decreases, right? So it increases in terms of ionization energy, and it actually decreases in terms of size this way. So fluorine should be the smallest, and sulfur would be the highest in that case. Electron configuration, periodic table, periodic trends. Any questions? All right, that wraps up chapter 11.